Hello and welcome to 13.6 Power Plants and the Electrical Grid. This is our very last lesson of the entire course, so enjoy it. We've learned all sorts of things about how to induce electric current using magnets. Now, this very last piece is looking at, on a larger scale, how we do that and how we get electricity from a power plant to our homes. Now, there's a big problem, which is that if we try to transmit electricity over some wires, let's say I've got my power plant, I've got my home, and to get the electricity to my home, I need to run that electricity along some wires. We are going to lose some power to those wires. In physics, we like to pretend that our electrical wires have zero resistance, but in reality they don't. They have some resistance, and if they have some resistance, and that means that they're going to consume some power. We're going to lose some voltage along the way, and that's not good. We don't want to lose any voltage. So in this lesson, we're going to look at how we can reduce that as much as possible. And it actually turns out to be pretty straightforward, and again, a very good reason why we use AC instead of DC when we generate our electricity. So let's get started here. Power loss. When current runs through a wire, some voltage is lost. And the amount is going to be based on the wire's resistance. Now we have an equation for that, which is equal to P equals VI. Now I want to stop here for a second to really point something out here, that this V here, this V is not the total amount of voltage that we're sending along the wire. Okay? I could be sending 10 kilovolts of voltage along the wire. Not all of that is going to get consumed. This V here is how much voltage the wires are eating up. Remember that voltage is basically how much energy we have to spend along the way, and we want to be able to spend some of the energy at the end point on some resistors, but some of the energy is going to be consumed along the way on the wires. So this voltage is not our total voltage, it is the amount of voltage that we're losing to the wires. So if we want to find out how much power we're losing, we need to first figure out how much voltage we're eating up on those wires. And here we can use V equals IR. If the wires have a certain amount of resistance R, then the voltage it consumes is going to equal I times that resistance. So we get IR times I, and that gives us an equation I squared R. And that's the equation we're going to be using here. This is how we can compute how much power we're losing to our wires. P equals I squared R. Now, for efficiency, you can see from that equation, if we lower our current, we're going to get less power lost. Lower current equals less power lost. And you can see that it scales quite a bit since we have I squared. If we can reduce current by a factor of 10, then we reduce power loss by a factor of 100, which is quite useful. Let's look at a few examples here. A generator produces 300 megawatts, which is 3 times 10 to the 8 watts, of power, at a current of 30 kiloamps and a voltage of 10 kilovolts. That power travels through a transmission wire with a resistance of 0.1 ohms. How much power is lost in megawatts and in percentage of the total? So first, our equation P equals I squared R. Well, I squared, here we've got 30 kiloamps. Kiloamps is 10 to the 3 amps. And I'm going to square that. And again, this, I want to point out, is the most common thing that people forget when they're doing these problems. They forget to square the current. So P equals I squared R. Our resistance is 0.1 ohms. This gives us 9 times 10 to the 5 watts. Oh, I'm sorry. It equals 9 times 10 to the 7 watts. Which is equal to 90 megawatts. The question says we want the power loss in megawatts and also in percent of the total. So if we do 90 divided by a total of 300 megawatts, we multiply that by 100%, we get a result of 30%. That's pretty bad. If you were a power company and you were losing 30% of your power before it even reaches people's homes, you're not going to be making a lot of money. So let's see if we can fix that. We're going to try to fix that with a step-up transformer. So now a step-up transformer is used to increase the voltage to 100 kilovolts before sending it over the wire. This lowers the current to 3 kiloamps. Remember this equation here. What is the new power loss? So you can see before we had 10 kilovolts, now we have 100 kilovolts, so we've multiplied by the voltage by 10, which means we've divided by the amps by 10. And in this problem, you've been given that 3 kiloamps, but often you will be required to just find that current on your own. Okay. First, P equals I squared R. We plug in our current, 3 times 10 to the 10 to the 3. We square that, same resistance, and we're going to get 9 times 10 to the 5 watts, or 0.9 megawatts. And you can see how that has made already a huge difference from our 90 megawatts before. If we do 0.9 divided by 300 times 100%, we're going to get 0.3%. From 30% down to 0.3%. The amazing thing is we're still transferring the same total amount of power. All we've done is, for a little while, we've said, let's transfer it at very, very high voltage and reduce the current a bit. It actually isn't a problem at all, so it makes a lot of sense to kick up our voltage very high near the power plant, transmit it at very high voltage, and then just step the voltage back down when we need it to be at a lower voltage. So there's a picture of that down here below. Here we have our power plant. So let's say we've got hydroelectric power, so we've got some sort of dam, maybe this is at Niagara Falls, and it's causing some turbines to spin, generating electricity, and maybe it's generating at 20 kilovolts. That's the raw generation. Right away, before we send that power anywhere, we step it up to a much higher voltage. So at our generating station, we step up the voltage to somewhere around 500 kilovolts, or maybe only 230 kilovolts. But we step it up quite a bit, from 20. So you can see that, that we're multiplying by maybe more than 20 times the original voltage. Okay, and then it travels along at that new high voltage for a while until we get to our district. So this is, the first layer of stepping the voltage down. We're going to go down to 115 kilovolts because we're getting near our destination. Then we get to our local transformer, and we're going to step it down even further. We get to the substation, and now we're getting very close to your home. So somewhere in your neighborhood you will have a substation like this, and that's going to step things down to just 4 kilovolts. And that's how the electricity is going to travel along the poles that you've probably seen where we're transmitting our phone lines and our electricity lines along some poles, and they're going to get to your house. Right before they go into your house, you're going to have a pole transformer. Something sitting up on the electrical pole, and that's transforming our voltage from 4 kilovolts down to what we use here, 120 or 240 volts. And that's the whole process from the station to your home. There's a few pictures to the right here of those different kinds of transformers. So you can see here we have probably a local transformer station, or maybe a substation. It might be a district transformer. I'm not sure which one this is, but this is one of the higher levels here. Whereas this would probably be a substation, or something very close to your home. If you live in a suburb, you've probably seen something that looks like that. And that's the idea. That's how our electricity is getting to us. That's how we avoid losing a lot of power on the way. Okay. There's one very last detail that was mentioned in your textbook that I thought was kind of neat, so I'll share it here. In our AC generators, sometimes instead of using physical magnets in our generators, sometimes we use a DC electromagnet inside the AC generator. Instead of a permanent magnet. And you can see how that DC electromagnet could even be powered by the generator in some sort of feedback loop. So it's interesting the different ways that we can modify this process to try to get the most amount of energy out of our system. Obviously, with the electromagnet, we can produce much more powerful magnetic fields, and therefore get a lot more current than we could normally get out of permanent magnets. So that was the last little interesting tidbit to get you thinking about how these generators work. We've got a few problems there at the end, and that's the end of the course. So enjoy that, and I guess I won't see you in the next lesson. Take care.